now we're going to change topic and we're starting to go towards gravity. So this is going to be a very different lecture from Anne-Catherine's lecture, and I think this is good because now you can see that there are different ways in which we can talk about quantum reference frames. So we are not going to see any group here in particular. So there's much more technical stuff under what I'm going to say, but my goal is to just give you the intuition, the physical intuition of these results. And the idea is that we want to generalize the equivalence principle to quantum reference frames. And I will make this more precise in the following. But first, let me start with talking about the usual equivalence principle and why it is important in a physical theory. So this is a quote from one of the most used books of general relativity, that is the gravitation book. And it says that the principle of equivalence has great power. With it, one can generalize all the special relativistic laws of physics to curved spacetime. And the curvature need not be small. So basically, in this quote, the authors identify not only the fact that the equivalence principle is a powerful conceptual tool that lies at the basis of general relativity, but also the fact that it is actually useful for building the theory. And so, for instance, statements of this type, so the world lengths of massive test bodies are time-like geodesics, that photons propagate along null geodesics, and that there is a link between the proper time registered by an ideal clock and the metric, these are all statements that depend on the formulation of the equivalence principle. And this is what I said. So basically, the idea is that since this is such a powerful conceptual tool that we use for the theory, then what happens if we are in a situation in which the usual equivalent, we are not in the assumptions of the usual equivalence principle? Well, we would still like to have something like that, so possibly a generalization, so that could maybe guide us towards building a theory of gravity in the quantum regime, or like something else. And okay, so in particular, the Einstein equivalence principle encodes the metric character of the theory. So now we have different types of equivalence principles. The ones that we're going to be concerned with in this lecture are the weak equivalence principle and the Einstein equivalence principle. So what is the weak equivalence principle? So it's basically the universality of free fall. Sorry, okay, better. So it's a universality of free fall. So basically, the idea is that if I have an observer that is the usual Einstein elevator that is in an accelerating elevator with constant and uniform acceleration A, then this situation is indistinguishable from a constant and uniform gravitational field that is the opposite of A. And the way you derive this statement is, so imagine that now we have F. So basically, if we have a force that acts on our system, then this system, by Newton's second law, reacts to that by accelerating. And the way so basically, the acceleration is proportional to an inertial mass of this system. On the other hand, if a body is in a gravitational field, then it couples to gravity with a gravitational charge. And the gravitational charge is the mass of this system. And in principle, these two things are conceptually distinct. So there is no fundamental reason why they should be the same. Because really, they come from two very different definitions. So for instance, the equivalent of the gravitational mass for the electromagnetic field is the charge, Q. So there is no reason why they should be the same. But the equivalence principle tells us that they are the same. And it has been measured that they are the same. So it's actually a very deep principle. So how do we test the equivalence principle? And I will need this in the following. So just if you don't understand, stop me. So when you want to test the violation, you assume that the weak equivalence principle doesn't hold. So you assume that the inertial mass is different to the gravitational mass. So for instance, a typical thing that you can do is you assume that the internal energy contributes differently to the inertial and the gravitational mass. And then you can parameterize this difference in the way that is written there by this eta A is a violation parameter, EA is the internal energy of some type of the system. A labels the type of internal energy of the system. And then you put this you write this equation there. Then you have to compare two different situations. This is very important. To have like a real test, a strong test of the equivalence principle, you compare the free fall, for instance, of two different masses, m1 and m2, and then you see how they are accelerated. So you compare, you take basically the relative acceleration, and then this is normalized. And this quantity here gives you a violation parameter that is called the Utvosh ratio. And if you, this is basically just a simple, so you can write this just by using that definition there, and you find this equation here. So you basically now you see that if one of these eta A is, so if one of these quantities here is different to 0, then you have an eta that is different to 0. And so basically, eta equal to 0 tells you that a weak equivalence principle is satisfied. Eta different to 0 tells you that the equivalence principle is violated. Okay. So what is instead the Einstein equivalence principle? So this is a different statement that again, one of the most common formulations says that in any and every locally inertial frame, anywhere and any time in the universe, all the non-gravitational laws of physics must take on their familiar non-relativistic form. So basically, this means that if I have a point in space-time, then I can pick any point in space-time, take a coordinate transformation, so that locally at that point, the metric is locally flat, so I get Minkowski, and the first derivative of the metric is also 0. Then, of course, from the second derivative onwards, you're going to have terms that are different to 0. And the non-gravitational part is also very important, because this means that, for instance, if you apply this, if you do an electromagnetic experiment, then you can apply the Einstein equivalence principle to it. But if you're instead looking at a Cavendish experiment where you're looking at the gravitational interaction between two systems, then the equivalence principle does not, the Einstein equivalence principle does not apply to this situation. So, okay, this is basically another way of writing it. So basically, you have a reference frame in which this equation, this is a freely falling frame, and then you can take a coordinate transformation to a general frame where you're going to have these gammas that are related to your coordinate transformation, so they're related to the motion of the particle. And analogously, you can define this G tilde quantity that is related to the Minkowski metric that you have in that initial frame, and basically, through the coordinate transformation, you find this other metric there. And the equivalence principle tells you that actually these tilde quantities are actually really the metric quantities of the theory. So basically, you go from a situation in which you have no gravity, basically, the freely falling frames, to a situation in which the gravitational field is present, tells you that the spacetime is curved, and basically, the way you transform, so basically the coordinate transformation gives you the form of the metric field in a general frame. So it's really powerful to really build the gravitational framework. So it turns out, and this is, so there is a longer argument to relate the Einstein equivalence principle, as I told you in the previous slide, to what I wrote here on this slide, that there are three elements of the Einstein equivalence principle that you should test if you want to verify experimentally this principle. So you can break it down in these three statements. They are not all independent from one another, so there are relations between these three statements. But it is important because this is a formulation that is more amenable to be tested in an experiment. So the first one is that the weak equivalence principle is valid. Then there are two properties that are local Lorentz invariants that tells us that the outcome of any local non-gravitational experiment is independent of the velocity of the freely falling frame in which it is performed, and then local position invariance that tells us that the outcome of any local non-gravitational experiment is independent of where and when in the universe it is performed. So basically, you take a freely falling frame that is locally at rest, this momentarily at rest with the particle that you're used to testing, that you're using to test the principle, and then in that frame, nothing should depend on the gravitational field. So then there is a very famous property of gravity that will be relevant in the following, that is gravitational time dilation. And this influences how a clock is measuring time. So the very basic statement is that if we're here on the surface of the Earth and we have a clock here, this clock ticks more slowly than a clock that is higher in the gravitational field. And this is something that experiments are testing to a greater and greater precision. So basically, this started with these fundamental experiments by David Wineland and his group. He got the Nobel Prize for that in 2010. This experiment was, where basically he just had these atomic clocks sitting on a table, and then he literally lifted the optical table by 30 centimeters, and he found that the rate at which these clocks were ticking was different because of gravitational time dilation. So this already looks like science fiction, but it's even more science fiction now because this type of experiment can now resolve the gravitational time dilation at the millimeter level. So it's amazing if you think about that, what the experimentalists can do now. Okay, clocks are a fundamental tool to test the Einstein equivalence principle. Why? So let us take just local position invariance to fix the ideas. And a paradigmatic test of local position invariance is the universality of gravitational redshift. So to test one single aspect of the principle, we usually assume the other two. So here we assume that the weak equivalence principle holds and the local Lorentz invariance holds. And for simplicity, we are just going to be in a weak gravitational field. We can write it like that. It's static. And we put two clocks at two different positions in the gravitational field of the Earth. And we know that they will tick differently according to their position. But we don't assume local position invariance. So we have an experiment in which one of the two clocks, here it's the upper one, emits a photon and sends it to the other clock, who receives it. And the two frequencies will be different because of the action of gravity. So the emission frequency is different from the reception frequency. In the freely falling frame, momentarily at rest with the clock 2, then I can write the line element, local Lorentz invariance, in this way. Okay? However, if local position invariance is violated, then this tells me that at the location of, so basically that the proper time of the clock in the freely falling frame that is momentarily at rest with the clock can depend on the position of the clock. And for instance, it can depend on the position through the gravitational field phi. So this, I can write the violation in this way. So this is the standard way of looking at the violation of this. So now I take a coordinate transformation, I transform to a static frame, so to a laboratory frame, for instance, and I will write my metric in this way, but I will still keep this violation parameter there. And now I write the emission and the reception frequency of the photon at the emission and reception point, basically by inverting. So basically the frequency is 1 divided by the proper time interval. So I get this formula, and since also the clocks are static, this is a particularly simple one, so I can write it in this way. And then I take it, and I want to get to basically to a violation parameter here too. And my violation parameter in this case is called Z, and I will write it as the reception minus the emission frequency, and then I just renormalize it by one of the two. In this case, it's the reception. And then again, I can take a first order expansion in 1 divided by c squared, and the quantity I get is this one here. So how do I write it in a more like revealing way? So I can expand the tau of phi emission. So I call tau of phi emission tau 0. It's just a quantity that I define. And then I Taylor expand the tau phi reception around tau 0. So it's, I assume that they're not very far from one another, so I can do a first order Taylor expansion. And this will have, say, 1 plus alpha g delta z divided by c squared. So this is going to be my expansion. And g delta z, notice that it's phi, basically. This is our gravitational field. So if I plug everything inside and expand to first order, I finally find that this z is basically has this form where alpha is my violation parameter. So now alpha quantifies how much the equivalence principle is violated. Good. So how do we make these two principles quantum? So, and why do we need a quantum equivalence principle at all? So when I describe both the weak equivalence principle tests and the Einstein equivalence principle tests, I implicitly assume that I had some classical probes. So I had, if you remember, I had these freely falling particles that were along a classical trajectory, and I had a clock that was also in a well-defined state. But if now let us take a quantum particle, and the quantum particle has a wave function. It does not have a trajectory anymore. The concept of trajectory does not exist in quantum theory. So it will follow some Schrödinger equation. Now I solve the Schrödinger equation, and I can write the state at time t as a basically using a Green function applied to the state at time 0. Now it is very simple to see that if you solve the Schrödinger equation of that Schrödinger equation that I wrote there, then the Green function depends on the mass. So now what I said before, that basically the universality of free fall, for instance, does not hold anymore, because the universality of free fall tells me that every particle falls in the same way regardless of the mass. So it seems that so the weak equivalence principle, as it is formulated in classical physics, cannot be applied here. So what should I do? I can either say, well, it's violated, or I can say, no, it should be extended to the quantum realm. Now, personally, I think that it should be extended in these cases here, because the equivalence principle is something that tells us something. Is a principle that tells us something about gravity, but here I haven't modified gravity. It's still the same gravitational physics. It's still, in this case, just Newtonian physics, and in general, if I think about GR tested with a quantum system, I still have GR. I'm not doing anything weird here. So I'm not in the assumptions of the classical weak equivalence principle, but because this was thought for a test with classical particles. So can we generalize it? And there are different ways in which we can see that basically the classical Einstein equivalence principle fails when, at least as I defined it now, when I test it in the quantum regime. For instance, the trajectories of the particles may be replaced by quantum states, or the reference frames attached to the particles or the clocks that I used to test it become quantum reference frames. So I could allow basically to take the view of a particle that is in a quantum superposition state. And then I do not know what happens. Or the internal energies that you remember were in the violations of the weak equivalence principle, this become quantum operator for a quantum particle, because, well, we have that, we don't have classical internal energy, but we have an internal energy Hamiltonian operator. Or this is even wilder, but gravity is quantum at some point. So there it's even more speculative what will happen. So, of course, like people have thought about the quantum equivalence principle since a very long time, and there are many different approaches, so there is no single way of talking about the quantum generalization of the Einstein, of the equivalence principle in any form, and this is just a non-exhaustive list of the papers that are out there. So you should be careful when you see like different, when you read quantum equivalence principle, because people mean different things. So we're going to see just one approach. And in particular, that is related to quantum reference frames, because this is what we are looking at in these lectures. So the easiest situation that we can consider is for the weak equivalence principle. So we have the initial quantum reference frame that is C, and then we have a quantum reference frame A that is in a quantum superposition of different accelerations. And then we have our usual quantum system B that both of them observe. So now I want to take an extended Galilean, so a superposition of extended Galilean transformations in the case of acceleration. That is the one that I also mentioned briefly yesterday. If I take this transformation, then what I would expect, if the equivalence principle holds, is that A is, well, in its own quantum reference frame, but C is B as if it was in a quantum superposition of uniform gravitational fields. So this is the situation that I want to describe, basically that I want to achieve if there is a generalization. So basically the statement could be that the equations of motion in a superposition of constant gravitational fields are indistinguishable from those in a quantum superposition of accelerations. How do I realize that? So I have to put myself in the conditions in which I can have a quantum superposition of accelerations. And, well, here I have a first difficulty because there is no acceleration operator in quantum mechanics. So the way we do that is to take a piecewise linear potential and prepare our quantum system initially in a quantum superposition of being in this, basically in this loop. So we have a coherent state that is much smaller than the width of the single slot of the same slope of this piecewise linear potential at the initial time, and a superposition. So this is a quantum superposition of another coherent state that fits completely inside a different slope. So now our assumption is that for the whole duration of this experiment, the state could spread out, but it's going to stay still in the same slope from where it started. So this, for the time of the experiment, realizes an acceleration operator. So that you can write effectively in this way. Of course, this is not going to hold forever. At some point, the state will be spread out enough that it goes out of the slot, but for the duration of the experiment, we assume that this is the case. So you start from this state, and now you have to come up with a quantum reference frame transformation that we can define, as I told you yesterday. And it turns out that this is really like a coherent superposition of classical transformations to an accelerated frame that is basically G1 in a superposition of G1 and G2. So we write it, and we find this quantum state. And in the frame of, so basically the particle evolves as if it was in a quantum superposition of uniform gravitational fields. And we also need to check how the Hamiltonian changes. And, okay, and the Hamiltonian changes in this way. So B gains, B that was initially a free particle, gains instead a potential that looks really like a quantum superposition of gravitational fields. So in this way, this is realized. It's realized that like the extension of the weak equivalence principle. What about the Einstein equivalence principle? So I told you about the definition that the gravitation book gives for the Einstein equivalence principle. Now you can take a generalization that basically the only thing that you have to do is to add a quantum in the definition. So basically you need to consider, instead of a local inertial frame, a quantum local inertial frame. That is a concept that has to be defined. And what do we mean by a quantum local inertial frame? So it can be two things. Imagine that we have the Earth and a particle that is in a quantum superposition of positions in the, on the Earth, so like a clock, an interferometric experiment where you have a clock that you send in a superposition of two paths, each one of which is in a different height in the surface of the Earth. And there, a quantum local inertial frame is the quantum reference frame associated to the clock, where the clock locally at the position of the clock, so locally in the sense of quantum reference frames, the clock sees Minkowski at its position, and also the first derivative of the metric is 0. But it can also mean something wilder. That is, let us consider a particle that is in a quantum superposition of gravitational fields and is freely falling in this superposition of gravitational fields, where freely falling is, of course, has to be defined relative to each amplitude of the gravitational field. And there I want to take a quantum reference frame transformation that makes the metric, again, locally Minkowski at the position of this particle. We are not going to talk about that. I'm going to refer only to the first situation. But let me just say something just to introduce the quantum superposition of spacetimes that Anne-Catherine is going to talk about extensively later. So what is a quantum superposition of spacetimes? So the honest answer is that we do not know what it is. Okay? So in the most general case, we don't have a rigorously defined notion of what a superposition of spacetimes can be. But we have some hint. Let us consider a particle that is a source of gravity in a quantum superposition of two positions. In this case, we have a formulation of gravity in the quantum regime that allows us to describe the quantum state of gravity of this configuration. So this is a very simple, simple quotes, situation, simple because we have a formulation. So it's basically, it's called linearized quantum gravity. You obtain it by linearizing the metric field. That is the same thing that you do for gravitational waves. And then by quantizing the perturbation about Minkowski spacetime. So that's something that is at least mathematically well defined. Of course, we can argue that there are still conceptual problems in doing that. I fully agree. But it's something that we can write down. And it's something that in the regime of tabletop experiments that are aiming at preparing this massive configuration, so this is, I mean, that's another interesting thing that I unfortunately don't have time to talk about, but experimentalists are actually trying to realize this situation in the lab by preparing a quantum superposition of massive objects that can be a source of gravity. That's a long-term goal, but it's something that at least now we can imagine. We can think that it is feasible, maybe in 20 years. And in this situation, linearized quantum gravity should be applicable. And we can write down technically the state of the gravitational field associated to this configuration. So in this case, if I have a particle here that is for all practical purposes classical, in a superposition with the particle being here, and again, it's effectively classical for all practical purposes, then I have a quantum superposition of geometries. Okay? So in this case, it makes sense to talk about that. But then I can use, I can extract basically the elements that I need to define this quantum superposition of geometries, and I can extrapolate them to a more general situation of which technically I have no clue about. So I want to extrapolate that to a situation more like this one. What are the assumptions? So the assumptions are that macroscopically distinguishable gravitational fields are assigned orthogonal quantum states. So basically the idea is that if I have a mass that is effectively classical here and it sources a gravitational field, and I can macroscopically distinguish this source from a source prepared here, meaning the states of the source are orthogonal, and I can distinguish them perfectly, then the configurations of gravity that I generate are also macroscopically distinguishable, meaning that they're orthogonal. And
And then they are, I say, so I'm allowed to say that they're macroscopically distinguishable only if I have macroscopic observables that I can measure and that can distinguish between these two configurations of gravity. So basically, if I put a clock, the clock should be able to distinguish perfectly between the gravitational field being in state A or state B. Then each well-defined gravitational field is described by general relativity, so I can apply the laws of general relativity for each configuration, and I'm allowed to use the quantum superposition principles for these configurations. All for now about superpositions of spacetimes, but this was just an appetizer. How do I test the quantum equivalence principle, Einstein equivalence principle in quantum reference frames? So, I told you that the Einstein equivalence principle breaks down into 3 elements that are particularly useful if you want to devise a test. So the same happens for the quantum equivalence principle for quantum reference frames. I have, we call them weak equivalence, QLLI, QLPI. And basically, again, you see that there is some quantum that I highlighted. And the idea, so the first one is the one that I already told you about. It's the quantum equivalence principle that we already saw. And the second one is that the outcome of any local non-gravitational experiment is independent of the velocity of the freely falling quantum reference frame in which it is performed. And the quantum local position invariance is that the outcome of any local non-gravitational experiment is independent of the position of the quantum reference frame in which it is performed. What does this mean? So, again, we're just going to look at QLPI because it's the simplest to look at. And so basically, we assume the other two, as we did in the classical test of the Einstein equivalence principle. We need a clock, but we need a quantum clock to do that. Because, of course, if we want the clock to be in a quantum state, we cannot have a classical clock. Yes? In which sense?
So, for example, if we, in this first part where you consider 2 clocks at different positions,
yeah,
and then they have a different proper time, you could argue that this is still kind of a gravitation experiment since they undergo different gravitational forces. I was just wondering how
no, what is meant is that so basically, instead of the clock, for instance, you could have some, so here you're directly testing the gravitational properties. And so that's directly the test of the equivalence principle. But what that means is that if I have an electromagnetic experiment, so I have a Cavendish experiment that tests the Coulomb force between 2 charges, locally, I should describe it with special relativity. So it's, yeah. It's not in contradiction.
So the clock experiment would be considered a gravitational experiment?
So the clock experiment is directly the test of the equivalence principle. So it does not really apply because it's like it should be an experiment in the frame of the clock. So you should look at something else in the frame of the clock. The clock experiment is non-local, just to start with. Okay, so we need to consider a quantum clock. What is a quantum clock? Well, this is really like the Mickey Mouse definition, so it's the simplest thing you can consider. It's an atom with some internal degrees of freedom. And for simplicity, we just assume that it has 2 different internal degrees of freedom. So the ground state and the first excited state is 0 and E1. And the difference between these two is going to be delta E. So now, if you want the system to function as a clock, you have to prepare it in a quantum superposition of the 2 energy eigenstates, simply because if it's just one of the 2, then the system is not going to evolve. You just have a global phase in front of the state, and this is not measurable. So in order to have a state that changes in time, then you have to prepare a quantum superposition of eigenstates. Yeah, and this is what I said. Then when you apply this Hamiltonian to the initial state, you get this relative phase. And then you say that basically the tick of the clock is when the state evolves to the state that is orthogonal to your initial state. So this T orthogonal, we call it orthogonalization time. And this is simply defined when this phase is equal to -1. That means that T is pi h bar divided by the energy gap of this clock. Good. But then we have something else. In special relativity, we know that the internal energy of a system contributes to its mass. But the internal energy in this case is an operator. So the mass becomes an operator. So now this sounds like a bit out of nowhere, but actually it's useful because we use this basically mass energy equivalence as an effective way of writing down the Hamiltonian of a quantum clock in a classical gravitational field. I don't have time to show you all the derivation, but there is actually a thorough derivation that was done by Magdalena Zich in her PhD thesis, where she shows that starting from the rest frame of this clock and changing coordinates to the laboratory frame, and she did all the calculations properly, basically you get a Hamiltonian that can also effectively be obtained by just doing this mass energy substitution that I showed you before, at least to the first order. So as a rule of thumb, you can remember that wherever you see the mass in the Hamiltonian without the internal degrees of freedom, you just add the internal Hamiltonian to the Hamiltonian, and then instead of wherever you see the mass, you put m plus h divided by c squared, and you obtain the correct Hamiltonian that you need to look at how the clock works. And then she showed, this is a very nice paper, where they consider a clock in a quantum interferometer. So the clock is in a quantum superposition of two trajectories in the gravitational field of the Earth. And they look at the interference figure at the end of this experiment. And remember, again, the slogan that lower is lower. So the clock in the trajectory 1 ticks more slowly than the clock in the trajectory 2. And you initialize the clock, as we know, it acquires a phase. And then at the end, what you do is you trace out the degrees of freedom of the clock, and you recombine the path to forget the which path information. So and then something interesting happens, that is, you have a reduction of visibility in the interference pattern at the end of the clock. And this is something you would not have if you did not explicitly add the clock degree of freedom to the description. So if you just have the path, if you just consider the external degrees of freedom going at the end of the interferometer, and then you measure at the end with a beam, you put a beam splitter, you forget which way information, then you don't observe any reduction of visibility. So you just have an interference pattern. And the reduction of visibility instead is important because it depends on the fact that if the clock is here or here, it encodes information of where it was in the gravitational field in its proper time. So here, basically, you can apply the complementarity principle, telling us that visibility plus distinguishability sums up to 1, and here you just see it very easily, to the fact that gravity basically, to the fact that the clock carries which way information in its proper time. And since it carries which way information, we have a drop in visibility. So this is the message. And this is what allows us now to use these quantum clocks for tests of the equivalence principle. OK, so now let us consider the situation in which we have a clock in a quantum so basically the same thing as we had before, a clock in a quantum superposition of positions in the gravitational field of the Earth, and another clock in the reference frame, in the laboratory frame of the Earth. So now we want to do the same experiment we did before. Imagine now this first clock sends a photon to the second clock, and in the quantum reference frame of this clock, it emits it with a certain frequency. And then we ask, how is the second clock going to receive it? What is the frequency of the second clock? So there is no well-defined frequency because the clock is in a quantum superposition of positions in a gravitational field. So in other words, according to the second clock, the first clock doesn't know how to tick. And then if we recall the argument that allowed us to derive the test for universality of gravitational redshift, we needed the freely falling frame momentarily at rest with the clock. but it is immediately clear that we have no single freely falling frame momentarily at rest with the clock in a quantum superposition of positions. So what do? Well, we take a quantum local inertial frame. So basically, we need a quantum reference frame that is for the clock that is in a quantum superposition of these two positions. And if we do that, so the calculations are very nasty, so I will not show them. But the bottom line is that the Z operator, that remember was the difference between the emission and reception frequency, and had a parameter of violation here that we called alpha, becomes an operator that acts both on the internal degrees of freedom of the clock and on the external degrees of freedom of the clock. In particular, it's diagonal in position. And so basically, and here it's as if we were saying that the internal energy of the clock contributes differently to the inertial and gravitational mass operator, and also that if we take the quantum local inertial frame associated to the clock, this clock knows where it is through the gravitational field, through the quantum position of operator of this clock. Okay, so now we can make a test of this. We will have two clocks just because we want to compare how these two clocks tick relative to one another. And in this case, for instance, I put them along the same trajectory, in an entangled state along the same trajectory, but we could also be more creative and put them in a different quantum state. This doesn't matter. And the measurement strategy is still the same. We have that we trace out the clock degrees of freedom, and then we recombine the path of the clocks at the beam splitter to forget which way information. And then what you find at the end is that the scalar product that, remember, was important for the visibility of the clocks at the end of the interferometer, the scalar product between clock 1 and clock 2 is what you would have if the quantum generalization of the Einstein equivalence principle was valid, plus a term that explicitly depends on the violation operator of the clock that we defined. And so, in the end, the probabilities at the end of the interferometer that are detected explicitly depend on the violation operator. So basically, when we collect statistics, if we make an atom interferometric experiment of the clock, basically, with these clocks, with these quantum clocks in the gravitational field, then we can use it to test the violations of the Einstein equivalence principle for quantum reference frames. So this is the bottom line. For those of you who are familiar with the Page and Woutert's approach, so in order to write the transformations from between these two quantum reference frames associated to the clocks, we need a covariant description. So basically, we need to be able to transform space and time. So we have, so we need to use a weird formulation that mixes a bit the Page and Woutert's with some covariant description of quantum mechanics. And if you know Page and Woutert's, basically, you know that we come up with a history state, okay, once we solve Page and Woutert's. So basically, what this, I finished. Yeah, this is the last. So basically, when you go, if the Einstein equivalence principle is violated, then in the quantum reference frame of the clock, it is impossible to write a history state. So we lose the possibility of having a history state if the Einstein equivalence principle is violated. So in a way, the validity of this generalized Einstein equivalence principle is also related to the validity of the perspective of the quantum reference frame itself. So it would be interesting to actually do this experiment. The last thing I wanted to tell you is that if you generalize the Einstein equivalence principle to quantum reference frames, this has a relation with the spontaneous state reduction that Penrose introduced. In particular, Penrose famously advocates in favor of classical gravity, And he has many different arguments, but the one that is more useful here is that the principle of linear superposition is incompatible with the principle of general covariance and the equivalence principle in gravity. So what he does is he considers a state of a mass that is put in a quantum superposition of different positions. And he says that there is no single coordinate transformation that makes symmetric locally Minkowski. And we have seen that, I mean, this is obviously true. And then he says, well, but there are different killing vectors. So basically, he doesn't even think that one can like quantum superpose transformations because he's using really general relativity. But he says that for each configuration of the mass, that there are different killing vectors. And if I have different killing vectors, so basically a killing vector is related to a conservation law. So basically, the global state has an uncertainty in energy. So there are different energies associated to each killing vector in the two amplitudes. And then he says, if I have a superposition of gravitational energies, then I have an unstable configuration. And hence, it should decay in a time that is roughly h bar divided by the difference in gravitational energies for the two configurations. So this is his statement. And then he says, well, if these two are actually incompatible, then I have to choose one. So he wants to put general relativity first, so he chooses the equivalence principle, he abandons the principle of linear superposition, and this leads to the whole modification of quantum mechanics that is the spontaneous state reduction. But then we have seen that this is not necessarily so, because what you can do is that you can quantum superpose the transformations. And if you do that, you don't need to abandon the equivalence principle or the principle of linear superposition. You can extend the Einstein equivalence principle to be valid for a broader set of assumptions, and this can be reconciled with the principle of linear superposition. Okay, so this is all. And this is my summary. So I started introducing a formalism for quantum reference frames that we call foundational perspectival, that is operational in the sense that we want to assign an operational meaning to the quantities that we write down, and relational. And basically, the core is that we associate a reference frame to a quantum system. And we make everything relational. And we have seen that it can be useful in quantum mechanics to look at the frame dependence of entanglement and superposition, generalization of covariance, and generalization of the weak equivalence principle. And then I told you, but I haven't shown, that this can also be helpful to operationally define the rest frame of a quantum system. In gravity, we looked at the generalization of the Einstein equivalence principle at Penrose decoherence, how this impacts Penrose decoherence. And more in general, and this is in preparation for Daniele's lectures, if gravity is not classical, we cannot have a classical reference frame. Of course, everything that we said so far is very different technically to what is done in quantum gravity, but as I think will be clear also after Daniele's lectures, there are some conceptual questions that are shared, and so the hope is that we can help each other to figure out each other's open questions that are many. And so this is good news because there's a lot of work for everyone. And you're very welcome to contribute. Thank you. Yeah.
Just wanted to ask how the visibility is reduced when you have like these two empiric clocks, right? Then you say that the visibility is reduced.
Yes, I think, I don't remember, but I think there is a square factor because you have two clocks. So the form is very similar to what you have in the... So wait, you meant the experiment by Magdalena, the quantum interferometric visibility?
Yeah, exactly.
Ah, okay, so there the visibility is really... Okay. Where do I have it? No. Here. Yeah, here. like that. So it's a scalar product between these two, the two clocks. So basically, if we didn't have a clock, or if the clocks told us exactly the same time, the visibility would be 1. And then as soon as the clocks start dephasing relative to each other, and they dephase with that phase, you have, so basically it's delta E times 1 minus the gravitational potential. And then this is the relative phase. Then you put it in these two initial, so the initial state of 1 is that with the, say that we set that to 0. The other one is with h, is gh divided by c squared. And then you put it in tau 2. And then you have to take the scalar product between these two. And so it's like a cosine of like gh divided by c squared, something like that. But actually, so the nice thing is that people are trying to do this experiment also now. So we are actually getting towards the precision in experiments that will allow us to test this. There are at least like a couple of groups that are trying to do it. Yeah.
I have two questions. Correct me if I'm wrong, and I think it's very basic questions. The last one is especially very basic. The first question is, in order to define quantum clock in your sense, I think my understanding is you utilize a kind of a transition process between these two energies, so that you assume that there is some extra field that arises that causes that transition. So I was wondering if you consider that kind of external field a different work in your discussion. That's one question. And the second question is rather simple. When it comes to this kind of discussion between gravity and quantum theory, the first thing that comes into mind is string theory. So I want to know the relationship between your discussion and string theory.
Very basic, yes. So, okay, maybe the first one is a little bit more, I can answer it more precisely. So, it's true, you need an external field in the preparation phase. So, typically, what you would do experimentally is that you need a particle in the ground state, and then you need to generate a transition to have a quantum superposition of the clock being in the ground state plus excited state. But then you decouple the external field. So once you have that, then you let it go. And so basically, what we are considering here, again, I said it's Mickey Mouse, because basically we had just assumed this whole thing has happened and it was successful, which for experimentalists is really not so trivial. And then we can just use it. But actually, what is true is that atom interferometers can do atom interferometry with clocks. And basically, this means that you send the particles in a quantum superposition of paths. You use some other degree of freedom to put them in a quantum superposition of paths. But in each path, you still have a superposition of internal energy levels. And this is what is your atomic clock, basically. So this is something that experimentalists can do. I'm very happy that they can do it. And I just use this. For the other question, so how is this related to string theory? No clue. So I actually wouldn't even know where to start to answer your question. So maybe one disclaimer that one should make in this case is that traditional quantum gravity approaches are usually set at the Planck scale and look at effects that happen at the Planck scale.